So, logistics-wise, things aren't much different from the first exam. You can still bring a cheat sheet with whatever you want on one side of a sheet of paper. This exam is over chapters 5 and 6, so the chapters about forces and Newton's laws. It will be the same kind of mix of conceptual and calculation questions, roughly about 1/3 of the points for conceptual multiple choice, and 2/3 for calculations. That's where you want to get a lot of partial credit if you can. And I'm going to go through the chapters quickly to say what I think some of the big ideas of the chapters are, and then we'll come back around to do some stuff from the practice questions. I did get emailed a few questions, so I'll go over those, but we'll also go over any that the people joining in live have. So let me start with jumping to the notes. So chapter 4, we introduce the idea of a net force pretty quickly. It's just the vector sum of all individual forces acting, and it is sort of an important thing for Newton's laws. It's one of the central bits. The first law is what happens when you have zero net force, meaning all the forces add up to zero effective force. In that case, the object's motion doesn't change. It will either keep rolling if it was already doing so, moving at a constant speed in a straight line, or it will just sit there if that's what it was doing. We call that property of stuff inertia, and so we call the first law the law of inertia. The second law is if you have a non-zero net force acting, meaning when you add all the forces acting on an object, you get an effective force. It's as if someone is pulling in a certain direction. That net force can cause accelerations, and the larger the net force, the larger acceleration you will see, meaning change in the motion of the object. If you have a more massive object, something really large, and you try and apply that force, it will not accelerate as much. And the second law combines those two observations to say the net force is equal to the mass times acceleration, or conceptually it's a bit easier to see it like this. Acceleration goes up if net force goes up, it goes down if mass goes up. It is our main tool for calculations in both chapters 5 and 6. It's the thing you keep seeing over and over and over in every question. So it's probably the most important for calculation of the laws. Conceptually, probably the most difficult of the laws is the third. It says how forces are connected to each other between different objects. So if you have one object pushing on another, then that will constitute a force, but there is also a push back on the original object. It feels a reaction to the push it's providing. And the third law says that those forces are always equal in size and exactly opposite in direction. So to sum it up, you push me, I push you back. Even if I'm not putting my hands on you, my body is pushing you back. And those forces are always equal to each other. Neither of us can push on the other harder. What usually wins out in situations like that is actually other forces like friction. But we do see that even when things are exerting equal forces on each other, you can see very different results, like me and the Earth. That's because our masses are different, and so our accelerations, the change in our motion that happens, is very different, but it's due to the same amount of force on each of us. This page is the most important thing to get down for math in especially chapter 5, but also chapter 6. This is your procedure for every problem. It almost doesn't matter what it's asking. You just resort back to this every time. And hopefully, as you go through some of these later bits, you'll see that's all I'm doing over and over and over. When I look at these specific forces, I'm just kind of telling you some features about them, but we still use this kind of method of analysis no matter what kind of force we're dealing with. So, some features of these forces. The gravitational force, all you really need to know about it is that it pulls straight down, and it's given by mg. That's what we see over and over. You don't have to worry about the general law of gravitation. So this is our specific case here on Earth. Weight equals mass times 9.8. Tension and normal force are similar in that they're just kind of whatever they have to be in order for the object to move however it's moving. What I mean by that is tension can be a big number or a small number depending on how hard you're pulling on the rope and how hard other things in the system are pulling on it. Normal force, same deal. You can have a large support force or normal force from a table, or it could be small, depending on what else is going on in that situation. So you call them constraint forces because they just kind of force things to move in a particular way. Normal force, you got to move along a surface. Tension, you got to feel a force that is along the rope. And that's their main features. So for the normal force, the most important things I can say for it are it always acts perpendicular to the surface, no matter what. No matter how the surface is angled or if it's upside down or sideways or anything, the normal force is always perpendicular to it. That's why we call it normal. The other thing I can say about it that people get wrong a lot, like a lot, is the normal force and weight are not the same thing, and they're not even always equal to each other. The very next example shows a case where this is not the case. Normal force can be bigger, smaller, or equal to your weight. It could even be zero, depending on what's going on. So you always have to look at the forces in the y direction, and you can solve for the normal force to see what's going on with it. You can't ever assume it's equal to weight. You got to do the work to check if it is. In many situations it ends up being, but you got to check. This is a pretty good kind of prototype example for stuff on inclines. So the main bit people forget is the direction you should draw your forces on an incline and these angles. So the quickest way is to just remember this, honestly. Maybe just draw this picture in your cheat sheet. If this angle is theta, the angle of the ramp, then the weight vector makes that same angle with the normal force direction, with that y-axis we've drawn. You can just always assume that. You could prove it if you want, but you could always just jump straight to that. You don't have to justify it to me. There could be one question on systems of objects, meaning you've got like two in the same problem. If that is the case, it will be very similar to this one. So if I choose to subject you to that, it will be very similar to this one. All right, chapter 6 is all about friction, the last of the main forces we talk about, besides springs, but that's not in this exam. And then it's also about circular motion. So main features of friction, there's two types, static and kinetic. Static is the stronger one, kinetic is weaker. Static also has the feature that it can grow in response to the applied force. The harder you pull, the harder it pulls back, up into this maximum static friction point. At that point, that's the most friction you're going to get. And then the object will start to slide and you're into the kinetic friction regime. That's what we call breakaway, and that's where we have a sudden drop in the frictional force. So static friction can be anywhere between 0 when you're not pulling and maximum when you're pulling at that breakaway point. After that, you jump to kinetic, and it's always given by this expression. At least that's a very good approximation in a lot of cases. Maximum static friction has the same formula, but with a different coefficient, and it will usually be a larger number than mu k to say that the static frictional force is stronger. This is just more of the same, free body diagrams, finding components of forces. The only new thing that gets added to the mix is what do I do with friction in my table? It's similar to weight. How I know I can always just say mg for weight, I can always say for kinetic friction, coefficient times normal force, meaning that right there. And so, very often in problems with friction, you're going to need to do this step with the normal force to figure out what it is for that situation. So, make it a good habit to always look at what's going on in the x and y directions, no matter what the problem is. It may help you out to just do all these steps, and then by the end of the problem, by the end of doing the steps at least, you'll look back at what it's asking and say, oh, well, I found that along the way. I won't make you do back to back, like look at all the forces and then do the kinematics. So kinematics is exam 1. We won't have it on exam 2. Just the force analysis of finding accelerations and values of forces and that kind of stuff. All right, circular motion. Main things that people forget about it are Velocity is not constant in circular motion because its direction is always changing. Its speed isn't, the magnitude of the velocity isn't, but you're always changing direction. And so you're accelerating. That acceleration always points towards the center of the circular path you're moving on. And so that means acceleration is also always changing direction so it can continually face towards the center point. Calculation-wise, all that gets added into the mix in this chapter is sometimes for your acceleration, you will have to say it's equal to v squared over r. That'll let you find some additional information that's specific to circular motion. So an example of that would be right down here. It's the same exact process as for any other situation, any other problem. You draw a free body diagram, find your components, set equal to mass times acceleration. The only new step is this right here. You put in v squared over r for the acceleration. The negative, remember, is just because that happens to be the direction of the acceleration in this problem. So it's the same rules as for forces. If the acceleration points to the left, you call it negative. If there's problems on satellites, it will be very plug and chug. As in, I want to know how fast a satellite's going if it's orbiting around a planet of mass big M at a distance r, and I give you the value of g in the equation sheet. So the only way this can go wrong is if you forget to look at the section that literally is labeled, this is for satellites. Like if we go to the practice exam, this is for satellites. This is for satellites. This is for a banked curve. So just use your equation sheet if you're not sure. It looks like there's not a lot here, but this is actually all you need for the chapter. 2 chapters. And to remind you what this is, I see this happen a lot. People think this is tension because we do have some overlapping variables here. This is period, the time for a satellite to orbit. So if you're asked how long it takes a satellite to orbit, you should be looking for this expression. And here's another one specifically for friction. So again, it's the same process, free body diagram, components, mass times acceleration in the x and y, the new step of saying that's v squared over r, and then include the direction with a minus in this case. And the rest is just like any other problem. So I really think of these 2 chapters as just start with that basic idea of analyze all the forces with a free body diagram and your components, and then chapter 6 just adds a couple layers to that of if there's friction, and then separately if there's circular motion. They're just add-ons to that basic process. And again, very plug and chug for questions like banked curves. I gave you that formula because the algebra is a little messier. Okay, that is pretty much the recap. So it's not a lot in principle. If you treat it like it's just all the same thing over and over, just apply it to different situations. And the main thing to practice here is just doing that setup of free body diagrams, components, net force equals mass times x and y, acceleration, so on and so forth. And that's why there's lots of those problems in the practice thing. So are there any initial questions? All right, well, if not, I did get some emailed in. They were about the solutions, just clarifying some things in them. So let's see. I'm just kind of going as I see the question. So question 35. The question was, how does acceleration keep changing direction if it is always towards the middle because it's a centripetal acceleration? So that's a good question. It seems contradictory to say it always points towards the middle and yet its direction is always changing. It's because if you're the object moving around the circle, where the middle is changing for you. You have to look over here to see it, and then over here, and then over here, and then over here, and so on and so forth. So your acceleration is always pointing that direction, but if you look at the vectors themselves, they're definitely changing their direction. So it does always point towards the center, but that forces the acceleration to continually change direction. Question 26. I don't get why the magnitude of the frictional force is 12 newtons. And they said, is it because it doesn't break the Fs max threshold to become kinetic friction? Therefore, if it's below 20 newtons, it's just the force applied. That's exactly it. That's a perfect explanation. So what we're checking here to see if the block actually moves is, what's the best case scenario for maximum static friction? Meaning, what's the hardest we could pull before this thing ever slides? And for that, we can use this formula. It turns out it's 20 newtons in this case. As long as we don't pull harder than that, the block will not slide. All it will do is keep up with however hard we're pulling. We pull with a 12 Newton force. That's less than 20, and so friction just keeps up with it. We just have a opposite pull from friction of 12 newtons to keep the block at rest. All right, question 6. It says, would it be wrong to say 2 and 3 because they are also an action-reaction pair? Let's see, a book on the surface of a table. They're asking if 2 and 3 are an action-reaction pair. The force of the table pushing on the book, the force of the book pushing on the table. Yes, they are an action-reaction pair. They're just not in that list. So if I drew a sketch of this, we've got table, book sitting on top of it. I'll color coordinate my action-reaction pairs. Earth pulls on the book. Book pulls on Earth. Those are equal and opposite forces. The force the Earth exerts on the book is the weight of the book. It's just another name for it. Another force pair. The table pushes on the book, and the reaction to that is the book pushes on the table. That's an action-reaction pair. The force the table exerts on the book and the force the Earth exerts on the book tend to be equal to each other a lot of the time. That's the normal force and the weight of the book, but that's because the book's in equilibrium. The forces on it are balanced. It's not about that the forces must be equal. It's not action and reaction, it's equilibrium, the first law, not the third, for those two. Some other action-reaction pairs. The Earth pushes up on the table. So we could talk about the force the Earth exerts on the table. That's another normal force. It would actually act through both legs of the table. The reaction to that is the table pushing back on the Earth. And then we could talk about the force the Earth exerts on the table, not through this supporting surface, but through the direct gravitational interaction. So Earth pulls down on the table. Table pulls back up on Earth. And there's even a gravitational interaction between the book and the table. But it's getting so messy here, I won't draw that one. All right. So lots of pairs there, but only one of the ones listed is an action-reaction pair. Okay, next question. I also don't get the next question on how it's 1 and 2 for number 7. Okay, so this was the thing I was getting at of, this is not the third law, this is the first law, because both of these forces act on one object, the book. They happen to be equal and opposite, not because of an action-reaction thing, but because the net force is 0. We know because the book's not accelerating. These forces have to balance, otherwise the book would go shooting off the table, either flying up in the air or falling down through it. If the forces are balanced, it just sits there. Question 40. How is t not 2, but instead 1/2? Because isn't it 2 spins per 1 second? So it would be 2. Okay. So, yeah, it tells us that it is 2 revolutions per second. And the question is, why does that mean the period is half a second? Because the period is the time it takes for 1 revolution. They tell us 2 happen in 1 second. That means 1 happens in half a second. And this is the number we're looking for, the time it takes for that complete revolution. This is the period. But a quick way to get that is to just take the reciprocal of whatever's given, as long as it's in revolutions per second, because then you get units of seconds per revolution. In other words, the number of seconds it takes per each revolution, the period. So it is 1/2. Question 49, why is the centripetal acceleration when plugged in for AX negative? Look at whatever's causing the centripetal force. In this case, it's friction. Oh, yeah, that's my dog. She might get upset. We'll see. So, in this case, static friction is the thing acting as the centripetal force, and so the centripetal acceleration points in that direction. That means it's also in the negative x direction. So that's where that negative comes from. It points to the left. For number 52, why are we plugging in Fn top when we were trying to solve for that one? We don't know it, but we know Fn bottom. It seems if we are solving for Fn bottom, it seems as if we are solving for Fn bottom, which we already know. Should we be solving for Fn top? Okay, so let's see. This question is, we've got a rider moving on a Ferris wheel. What's the magnitude of the normal force when he rides through the highest point? So what's the magnitude when he moves through the highest point? So we're trying to find Fn top. That might be a good question. Let me look back through what I was doing here. So at the top, we've got our equation for the normal force, because we've got weight acting downward and normal force acting upward. And we have acceleration downward towards the center. That's why this is negative. And I say that means if I solve for Fn top, it's weight minus mv squared over r. At the bottom, I do the same thing, but now my centripetal acceleration is upward because it's still pointing towards the center. And so I solve for Fn bottom. That is this right here. And then when a rider moves through the lowest point, normal force is 684. I think I just did some bad algebra here. I think that's all this is. So this is a fix I need to make. So they gave us Fn bottom, and we want Fn top. Is that right? Yes, okay. So if I solve this for Fn top, it's 2mg minus Fn bottom. And Fn bottom was the one that was 684 newtons. But if we do that math, we'll realize I still get 394 because effectively all I did is I mixed up Fn bottom and Fn top in this final substitution. So, thank you for catching that. That one was Herschel. Credit to him for that. We'll call it extra credit. So I'm going to send out a fix for that one. And, I mean, it'll just be an email since it's a lot for just fixing this one question. But, yes, I did have those backwards on this one. All right. Any other questions?
Just some general ones.
Mhm.
I don't know if you said already. How many questions will be on this exam?
Good question. I have not written it yet. That's going to be my
Oh, okay.
weekend. But it's never any more than 14. Usually sits closer to 10 to 12. It just depends on what questions I choose and then how I want to distribute the points. And that's always sort of it changes every year.
Oh, okay.
It's sounding like we're comfortable with this. Maybe one thing I'll mention for the circular motion is questions like these are pretty typical conceptual questions as far as like what's the direction of the velocity at a certain point. It's going to be tangent to the circle. What's the direction of the acceleration? Towards the center. Or what's the direction of the net force? Towards the center. So it's asking the same thing in just a lot of different ways. And you just got to be careful not to let me trick you on which way I'm asking it. It's similar to with when we kept saying gravitational acceleration is always 9.8 down. I have a lot of different ways I can ask that to make it not obvious that's what I'm asking, unless you just know it in your heart. So, if this stuff is comfortable, doesn't matter how I ask it, you'll get it right. If it's not, I may be able to find that one way that'll get you. So, don't let me.
For centripetal motion,
Mm-hmm.
why is the net force towards the center again?
Because if you don't have a net force towards the center, the object's just going to keep moving in a straight line. And so you can think of the centripetal force as something that keeps yanking it back onto a circle. It would rather go off in a
Oh,
straight
so like
line.
with the string.
Yes. Yeah.
Okay.
Oh, so for this one, if you looked at it and said, "Oh my God, I have to do this on this exam," no, this is like a worst case scenario. Like, if you can do this, you will have no problem whatsoever with the exam. I'm not expecting you to, but it does put a lot of different things together all in one problem. So it is a good one to kind of understand all the ideas in, but it's not the kind of problem I might ask you to do. It would be more like, so it could be one like this. This is a system similar to the one that's in the notes. Or I guess just that one that's in the notes. If I ask a question about a system of objects, it'll be like this or like the other one. So you can always email me if you have something pop up, and I will get back to you as soon as I can on that. Be working on these practice problems. I always think doing practice problems is a faster way to learn this stuff than rereading the notes over and over. And if you stop and find yourself, you know, chat GPTing or Chegg or something else for these, just realize that won't be there on the exam, and it can help if it gives you one step and then you take the next step, or you use it to just kind of get through some block. That's great. It can't help you if you have it spit out an answer and you read through it and say, "Oh, that makes sense," and then move on. Because sure, it makes sense when it's laid out in front of you. Your brain doesn't do that automatically. You have to write all that stuff down, which means it has to make sense in your own brain. That doesn't connect as well, I think, just having it print out. I say that from experience. That's not just a old man yelling at the clouds or something. All right. Well, I will see y'all on Tuesday.